Dear ladies and gentlemen, welcome to my virtual presentation for the IEEE Sensor 2021 conference. My name is Ivan Kraljevski and I am a research associate at the Fraunhofer Institute for Ceramic Technologies and Systems, IKTS Dresden, Germany. Also, I am a member of the project group Cognitive Material Diagnostics, COGMAD, which is located at the Brandenburg University of Technology, Cottbus-Senftenberg in Germany. On behalf of my colleagues, I would like to present you our study about autoencoder-based ultrasonic NDT of adhesive bonds. We present an approach for ultrasonic non-destructive testing of adhesive bonding employing unsupervised machine learning with autoencoders. The models are trained exclusively on pulse echo ultrasonic signals on one specimen with good adhesive bonding and tested on another specimen with artificially added defects. The resulting pseudo-probabilities indicating anomalies are visualized and presented along to the C-scan of the same specimen. As a result, we achieved improved representation of the defects, providing a possibility of their automatic and reliable detection. The specimens are constructed by bonding of 4 aluminum sheets with 2 mm thickness each. You can see the recording setup which was used to record true transmission C-scans of a specimen with, without and with defects, cavity and adhesive stripes. The objective is to perform NDT with a 5 MHz ultrasonic transducer from only one side. The specimens are scanned over both axes, the 310 mm and 150 mm with a 2 mm stride. For the training and validation, 5,520 samples are selected from the central region of the specimen where the adhesive bonding was successful and most consistent. As features, we use the raw transducer readings signal as analog signals converted to the big endian PCM format and 16-bit resolution. With a duration of 20 microseconds and a sample rate of 25 megasample seconds, the samples have dimension of 500 points per grid point. The signals are realigned by a trigger that finds the positive amplitude onset greater than a preset threshold. There are variations in the thickness of the bonding layers across the objects and unwanted reflections from the object edges. In order to compensate these effects, additional feature analysis, PFA, using the raw signals were performed. The PFA features were created by calculating the log magnitude spectrum with a Blackman window with a length of 75, yielding features with a dimension of 87 × 16 per grid point. We employed autoencoders, which are deep neural networks whose architecture consists of two parts: an encoder that transforms the input to a compressed representation, and a decoder which approximately reconstructs the input data as well as possible. The autoencoders reconstruct the input by minimizing the mean squared error. When an anomalous sample is tested, it will fail to reconstruct it successfully, producing a higher than expected mean squared error. The employed architecture consists of 3 hidden layers with 250, 150, and 250 neurons respectively. Both encoder and decoder layers use hyperbolic tangent activation function and root mean squared propagation as gradient-based optimizer. To avoid overfitting on such a network with relatively small capacity, we used early stopping with a criteria of 5 epochs without improvement in the loss of the validation set. We defined the deviation score from the normal state as mean squared error of the input sample X transformed into pseudo-probability of X belonging to the normal states. The input sample X is considered anomalous if this pseudo-probability falls below an estimated threshold theta. The performance of the models trained on only signals from the good specimen was measured by the percent of samples outside the threshold. The threshold is defined by the interquartile range. We can see on this slide on the top left the reference true transmission C-scan. Bottom left is the normal pulse echo C-scan with usual post-processing to reduce signal fluctuation, such as cut-in time, root mean square averaging. Because of the signal fluctuation, some defects are not detectable at all and are marked with a red rectangle. On the right side are the visualization of the pseudo-probabilities obtained with autoencoder trained on signal, right top, and the PFA, right bottom features. The brighter spectral colors indicate a higher probability of anomaly or defect. Both autoencoder models exhibit better representation of the defects with high contrast against areas with proper bonding. As a conclusion, we can say we investigated ultrasonic NDT with autoencoders trained on pulse echo signals to detect and visualize defects in adhesive bonding. The models are trained on signals from only one specimen with a good adhesive bonding and tested on signals of a specimen with incorporated defects. The process is entirely automatic and reproducible on other specimens once the autoencoder model is trained. The pseudo-probabilities have absolute values between 0 and 1, which are easily interpretable and suitable from anomaly detection using a calculated threshold for decision. There is no need for intervention by a human expert for setting analysis parameters, which is considered challenging due to the signal fluctuations. Future work will aim not only to reliably detect defects, but also to classify them by the type. Thank you very much for your attention. Feel free to contact me via email. I will be pleased to answer your questions. Goodbye and have a nice day.